experienced this at tabled events. A lot of times people are using the word air purifier, and I feel conflicted because I don't like perpetuating the idea that academics are super nitpicky about language, but I really don't like air purifier. I prefer air cleaner. So as much as possible in a proactive way, I think we can use air cleaner instead of purifier, or I can. I'll just speak for myself. But when people say air purifier, if they ask you, what kind of air purifier should I get? I think their domain in their brain that's referring to air cleaner or air purifier is the same. It's the same thing they're recalling. Probably I think the most useful metric is the CADR, which is the clean air delivery rate. It's often expressed in CFM, meaning cubic feet per minute, so the amount of clean air that can be delivered. And the nice thing about the clean air delivery rate, one nice thing is that it both is very useful for comparing devices in a way that people are used to comparing consumer products. So I think it's a very useful normal person metric, but it also can show up in a mass balance. So you can use it when we talk about how an air cleaner is performing in a mass balance approach to thinking about a room or a home. And so I like that. Commercially available portable air cleaners are, if you look for them online, you will often find that they report a CADR in cubic feet per minute for different types of airborne particles, or yeah, and they'll name them smoke, dust, and pollen. And those are nice terms because people know what those are, they can visualize them. And I think that's one of the reasons I believe, I haven't tested, I don't know this, but I think that one of the reasons that's used is because when people read, this will give you this much clean air for smoke, they know what that means to them, or they might care about pollen, or they might care about dust. What it translates to, if you were testing this in a lab, is particle size roughly, with pollen being large and smoke being really small. And ANSI, AHAM, which I always forget what those stand for. I'm sure Paul knows, and maybe Christian and Tammy and others, but they're like standards bodies. They have a protocol for testing the performance in terms of clean air delivery rate for these different classes of or particle size ranges. I have been hearing a lot, so I'm sharing this approximation or rule of thumb. I hadn't thought about it this way, but people that are more in like the implementation space have been picking up on this. I think it must be in some articles and maybe on EPA's website and AHAM. 100 CFM of clean air delivery rate is enough for roughly a 250 square foot room that has an 8-foot ceilings. I think there's been some interest in this because of the DIY, the do-it-yourself air filters, and the CADR that they can deliver for a certain room size, and wanting to apply that in low-income settings or settings where people may have a small space that they can keep clean. So I think that's one of the reasons this approximation has emerged. There's also within Energy Star realm, and I'll come to that in a minute, they have an integrated energy factor, which is a CADR per watt. So you have some idea of the clean air delivered and the amount of energy you'd have to expend to get there. California also provides ozone output. So if you're looking at air cleaner rankings, California provides information about whether ozone's being generated. That's a separate topic that I don't think we really need to get into here, but some air cleaners remove particles, but they do it in a way that also has a byproduct of ozone. And that is worth being aware of. I think most people on this call are probably already aware of that, but that's not just a downside, those are air cleaners that I think we should never recommend. And California feels the same way. So they call that out. But Energy Star and AHAM, I don't know I think you might have to dig for that information. Okay, there's probably more that could be said about how we define an air cleaner, but I'm just going to move on to some recent literature. This is a very text-heavy slide that I'm hoping people will just use as a reference in the future. I pulled papers that came out in the last 3 years. These are just a few. Their titles are down here. So their titles, I think, are worth saying a little bit. One was characterizing the performance of a do-it-yourself box fan air filter. One was real-world effectiveness of portable air cleaners in reducing home particle matter or particulate matter concentrations. So the first one helps you understand how these box fan filters are characterized, and how a DIY one is characterized is very similar to how you might characterize a commercially available one. So if you want to see what people have learned in the last few years about real world effectiveness, that's what this Liu et al. Paper and their real world trial was in 29 homes. PM 2.5 was reduced by about 50 to 60% with these HEPA, high efficiency particle air portable air cleaners. They have a 300 CFM unit that was equivalent to about a 10 ACH or air changes per hour in a 15 by 15 foot bedroom. Pretty big, I think. But it shows like you can cut PM 2.5 concentrations pretty considerably, 50 to 60%. Of course, it matters what your starting point is. Usage and impact of do-it-yourself air cleaners in a smoke-impacted community. The reason I highlighted this one is because I actually think this was interesting to see. I'm highlighting here. Participants favored commercial devices over DIY devices because of noise and the unwelcome cold draft during winter use. Like, this was a study that looked at DIY and commercially available cleaners, and their community, they report preference for this for commercial units. I think a lot of it has to do with noise. In other studies, people have pointed to noise as an issue for the DIY filters. And then there was this study that I wanted to highlight because they relative to the field, they did long-term performance. So they had about 1,000 hours of performance, and they could show that the CADR declined over that time, which you would expect because we expect to have to change out filters. And so this was sort of to me, it underscores the filter replacement schedule being an important part of thinking about long-term operation of these portable air cleaners, whether they're a DIY version or a commercially available version. The filters are not going to perform the same for forever. Okay. Moving on to selection guidance. So because there's been such an interest in both the DIY and commercial space, I think it's become easier to find selection guidance. I think, I don't know the history as well. I'm guessing that a lot of this might have been already in place. It's just a matter of attention and prominence or salience. But this 2020 AHAM protocol is a reference for the CADR test, like how to determine CADR. There was an addition in 2022 for virus removal, and a version that covers sound, because especially in the DIY air filter case, noise became a complaint. Energy Star has a database. I was going to put the links in here. I don't think I have them. Christian, in that separate project with Katie Dickinson and Kathy, I have links to like the Energy Star and the AHAM and the California like selection guidance resources. Again, I don't really feel for this study, we're trying to necessarily pick, well, I don't know, maybe we are, but we might want to at least know how these selection tools work. They haven't been developed so they're like super easy, user friendly, but they're like drop down menus, filter by X, filter by Y, compare products. They're not terrible. So commercial portable air cleaners stand in contrast to what not in major contrast, but I think there are sort of two threads here. There's commercially available ones, and then there's DIY portable air cleaners. And those sort of, came onto the scene because they were quite a bit cheaper in the initial reverberations of the COVID pandemic. Buying 1, 2, or 4 filters and taping them basically to a box fan was certainly cheaper, and you could do it like that day, right? You could go to Home Depot, you could buy a box fan and some filters and tape it together. And I think there was a degree to which people valued the immediacy of being responsive to their own conditions, that and then that was sort of bolstered by the Corsi Rosenthal box, which got a Dr. Rich Corsi and Jim Rosenthal um, put out some designs for 4 filters. It's a cube with a box fan. And there's lots of resources you can find on how to build this for yourself. Um, and it does really well. It was delivering a high CADR, and on a per dollar basis, it was out competing commercially available filters. As costs of supplies have risen over the last 3 years, and the cost of commercial portable air cleaners have dropped or at least stabilized because of competition, I don't think that the gap is as large in terms of cost. And then there's these added downsides of noise and people being unclear about filter replacement and whether you're actually like what the savings are over, say, a year of operation. I haven't actually worked out numbers lately, so I don't know. DIY filters may still break out ahead on cost alone, but I think whether or not it suits your purpose really depends on like access and how easily you want it to be put together. Whether you're kind of remotely supporting a team that's putting things together, and so they are just going to Home Depot or ordering things on Amazon, or if people want something that looks nicer and that they can like name and treat like a robot. There's variety of ways in which people want to use these. So sometimes I think DIY filters end out ahead and sometimes not. Um, there are versions that are single filters, so you just put the filter on the box fan, or 2 filters, so it's like a wedge. It's like 2 filters in the box fans here. So it's yeah, like a wedge. Those deliver less clean air. Their CADR are lower than a 4 filter version, but they may still suffice for the size of room that you're trying to treat the air in. So in some studies, they've been presented as a reasonable entry-level cost option. And this is just to give you an idea of what those actual costs are. These I have pulled lately, like earlier this week. So the cost per CFM, sorry, I said that in reverse before, normalizes price against delivered clean air, and a fresh Corsi Rosenthal box. So Corsi Rosenthal box is the cube. It has a box fan on one face, and then it has at least MERV 13 or better filters for removing particles. And then in 2025, it's around 25 cents per CFM. Popular Energy Star units. So if you go to the Energy Star database and you look for units based on dollar per CFM, and the CFM here is clean air delivered CFM. These are a few brands, the Levitt and the Blue Air. There are many actually out there. So I am not promoting these, but just to give you an idea of where they sit, it's about 60 cents per CFM. And so I would say the available databases are pretty good in terms of getting the cost and getting the performance, the reported CADR. I think there's some evidence in the literature, which is why I'd highlighted that CADR goes down with time, so that's worth considering. And then the CADR is going to be different between what you're trying to remove. In most of our conversations in this project, we've thought about smoke. But we could think about dust or pollen as well. Although, again, that's not really, dust and pollen are not going to be our major heavy hitters in terms of what's infiltrating from outdoor events. So I still think smoke's the worthwhile CADR to think about. So hopefully, if you didn't know these features about portable air cleaners already, is giving you a few thoughts to consider. I think commercial versus DIY is one distinction to keep in your brain. CADR is a good metric to be familiar with. If you want to know more about how it's constructed, there are resources to sort of show how that performance is assessed. That's a useful metric to then normalize against cost or energy use, and to be able to compare DIY to commercially available cleaners. And almost all of this information, I would say, is readily accessible by anyone. So people in our study might be able, would be able to go online and compare what they're getting or different things that they might want to get. So I think being familiar with the kind of information they would encounter if they were searching for this stuff online themselves is useful. I think I still went over 10 minutes, Paul. I'm sorry.
Yeah. All right. Thank you, Allison. I'm just going to jump into mine, make sure we get through all of these, and hopefully we'll have a little bit of time for questions and comments at the end. So I want to thank Misa for preparing these slides. I've trimmed from what you sent me, Misa, to try to squeeze it into a shorter amount of time and focus on the main points. But so Misa has done a lot of work on the fan and filter stuff all along. But we did a little additional work in part because now we know what fan we're going to be using, and we're trying to figure out which of the various filters we've procured seems to be the best one with the actual fan, not just based on various fan curves. And also think about what happens if we can't fully pressurize. Is it still worth doing anything? So first slide I've got here is this one where what this is about is kind of what was the performance of the different filters that we have procured with the fan that Jordan has been using. That's a key thing, with the fan that Jordan has been using. That fan nominally should be delivering about twice as much flow as it actually is, given the pressure drop across the system. But we still see a pretty large difference between flow rates. We see with the filter we were originally hoping to use, we're just over 125 CFM. That is just not really enough. That's why we started looking at other filters, going to deeper 12-inch filters instead of 6, but it's still all HEPA. And so there are these three over here that are near 200, one of which was just a little bit higher than the rest, right at almost 200 CFM. So that's likely the one we're going to be going forward with. Although it's not a huge amount of difference, as long as you're using 12-inch, we're like between 187 and 199 CFM. So really the 12-inch makes a huge difference, and it doubles how much what kind of stack effect we're going to be able to counter as we're trying to uh, pressurize these homes, which is really important. But so there's still a question. So if the fan only moves about 200 CFM, then if a house has more than about 100 CFM of infiltration, I'm just going to assume no wind, so it's stack effect only. It can only pressurize fully a house with about half of the CFM of the fan. So we're only able to do about 100. That's still going to be more than a lot of homes, but it's going to fall short in many homes, at least under colder conditions. So then the question is, how much benefit do we get if we can't fully pressurize the house? Is it still worth doing? So I'm not going to go through these equations. I'm just basically here. We're looking at two different things. One is over time, given assumptions about how much filtration the house is providing and how much filtration the filter is providing and how much airflow is going through the house and how much air is going through the filter, what is the concentration over time and what is the steady state concentration? Like if yeah, we're getting something for the first 10 minutes, but after an hour it's just as bad as if we didn't have the filter at all, it's not worth doing. We are assuming that the house is about MERV 9. Ellison talked about MERV 13 for the DIY boxes. MERV 9 is nowhere near as effective on filtering particles. That is the rating you get if you get about 65% of particles in the 1 to 3 micron range, and there really isn't any meaningful removal of less than 1 micron. But we're going to focus here on the 1 to 3 microns because we know if you don't have meaningful removal of under 1, then whatever we do is better. So we're going to focus on the 1 to 3s with a removal efficiency of about 65%. So this is how it turns out. This on the y-axis, that is the fraction. Like if we run the fan and filter, what is the fraction of the indoor concentration? Like if we didn't have that, what would the concentration be? And then what fraction of that do we have by running the fan and filter? Now we have a number of cases here. These different lines correspond to different infiltration rates. So anything that's up to about 100, so that's all these ones down to zero, anything that's up to about 100 CFM of infiltration, we're able to fully pressurize. And so because we're able to fully pressurize, we're getting everything. Then as we go to 120, 140, 160, 180, and 200, what happens? What we see is that even at steady state, we're still getting, at steady state, we're at about 35% of what we would have had if we did not have the fan running, even when the house is twice as leaky as it would be as we can fully pressurize. So when the house is equal, has leakiness equal to the fan flow, we're still reducing the concentration indoors by about 2/3 at steady state. And this is in minutes. So this is 1 day worth of simulation. So it takes about 6 hours to get to steady state, maybe a little bit longer. And um, and then it stays that way through the rest of the time. So what we're seeing is that relative to just a house only, we're still able to get a significant amount of reduction. This is where we actually went up to 400 CFM for stack infiltration. That's a really, really leaky house on a very, very cold day. You don't see that very much, but let's look at the kind of extremes. Even with that, we're able to reduce the concentration by about 40%. And so, um, you know, we, that was, it's independent really of the outdoor concentration because it does scale, but it's really based on what's the ratio of the uncontrolled infiltration, the fan flow, um, and it is considering the house volume and time. So really what we found was that, yeah, we can get up to about 200 CFM with the best combination of filter and fan, and that we are really able to get a significant amount of filtering out of that. And one of the things we talked about, but which I did not put a slide in, is that the cost of running the system and the durability of the system seems to be good enough that it's just, we should just run it. If there's an indication, even if it's really cold outside and we can't fully pressurize, we should just run it and get whatever we can. It will be a noticeable improvement. Sometimes maybe it won't have been enough of an improvement, but overall it should be a benefit much more frequently than not. So Christian, I'll bump it over to you and we'll see what time we have for questions.
Well, so I'm going to talk a little bit about the window unit we've been working on, and then some status updates on a few of the other tech pieces that have been on our plate. So first, just kind of as a reminder, this window unit design is the idea of doing something similar to like an in-window air conditioning unit. This does not involve a permanent modification to the house. It's probably not the most ideal situation for a productized solution here, but in terms of the scope of our project and the benefits of not needing to drill to people's homes, it seemed like a worthwhile thing for us to continue doing. The design has changed a little bit since some of the team has seen it, where we've reoriented the blower and the filters to be on each side of the window, so essentially sandwiching the window in between. This ended up being a lot better design when we started putting the first concepts together purely from a weight distribution standpoint. So that's just a quick note for those who have seen versions of this design before. We've been working on making this design appropriate for both vertical sash and horizontal sash windows. Prototype we've done so far, we've been working with uses sheet metal and a hemmed edge for each of these. So these are commonly made features on sheet metal, so they're super, super cheap to make. Where we hem one component slightly larger, that allows our kind of unit that the blower and fan is going through to slide with the other parts. This is what allows us to expand and contract the width or height of the system to accommodate different people's windows. And then with a simple sheet metal hand tool, you can actually crimp these two hems together, and they are shockingly well held together. So this means we wouldn't need screwdrivers or rivets or drills or any of those things. We would go to each home, slide to the right size, crimp and move on. So far that's worked pretty well on the prototypes. And then probably backline this metal with some foam, which is not the most aesthetically pleasing, which is again one of the reasons why we probably wouldn't do this as a long-term product, but helps on the temperature comfort side of things, because it's not just a thin sheet of metal. One of the biggest challenges is the weight management, because these fans and filters are not super light on their own. So what we've been working with is actually these support arms used for air conditioning units. So they're designed actually to hold, in some cases, 100+ pounds. But they've been working pretty well for our concept so far. So the concept of how these work is one side of this goes inside the house. We have the window transition, and then we have this counter arm that comes down that acts kind of as a lever to help distribute the load. Being really conservative with our numbers, rounding absolutely everything up, using the heaviest filter I could find in Paul's lab, and adding a 30% safety margin, we end up about 30 pounds-ish that we need to be able to account for, which is light for this sort of balance arm, but is heavy enough that we need something to help support it. These arms are pretty cheap, they're about $20, and so far have worked quite well. And so this actually transitions through that sheet metal part that I was showing before. Some constraints on the design as it stands right now is we need to be able to open the window at least 11 inches, and it has to be a sliding window. So like a crank open kind of pivoting window does not work with this design. You have to be able to fully open, which is a downside. As I've designed it right now, the maximum that we'd be able to fill the space on is 48 inches, but we'd be able to modify that if we need to do so. And then I guess I haven't updated this slide since I showed it to the tech team. We've modified the design a little bit so that there's actually pressure ports and power pass through on these sheet metal parts. So we can actually use this window shield for taking measurements inside and outside the house, moving power to the right places, all of those things. I do have one request for the team, is if you could go to your house and at some point measure windows that you have in your home that might be appropriate for design like this. And this isn't a commitment for you letting me install one in your home, but just to get some reasonable sizes of windows to make sure that we're covering enough of a range with this design. I don't want to undersize something and not make it actually appropriate for what we might need to do. Thank you, Will, for already sending over your numbers. That was hugely helpful, and I actually made some design changes because of that. So thank you for that. But if others wouldn't mind doing the same thing for me, that would be hugely helpful. If you're not sure what I'm asking for, I'm happy to send you a photo of the specific dimensions that I'm seeking to get there. Cost and time projections. One of the upsides of this is the fact that it's pretty cheap. So depending on how many parts we need, which is essentially how big your window is, all in for this, not including the fan, because it's the fan, we have to, fan and filter to have that for both designs. We're about $99 to $127 all in to put the system in place. So a pretty low cost investment. I found some nice adapter flanges to be able to go through these sheet metals to be able to actually connect to the duct and to the fan. So that was one of the outstanding items from the last time the tech team met. Danny was looking at 3D printed options, but I still think might work in some cases, but I have found off-the-shelf parts that will work for our transitions as well, which is what I've been doing so far. I did a first verification design and it worked pretty darn well, but I was a little too optimistic on the stiffness of the metal. So I'm making a new one now, which is just a little bit thicker and a little bit looser tolerancing on those pens just to make my life easier. So far, I've been making these by hand in the powerhouse basement, which is not a great thing that I want to do for the whole study, but at least it allows us to go quickly on prototyping. The prices I've quoted here are using a fabrication house to make the parts. So I think they're pretty realistic costs. I'm going to move on to a couple of the other components just for the sake of time, and then I'm happy to jump back to these if there's questions. I also see there's some things in the chat, but I can't look at both at the same time. We've been making some modification to the measurement nodes. These are like the boxes that we've been sending out to houses to address some of the concerns that were raised. The first is dealing with the temperature. As I think several of you saw, the temperatures were elevated in these boxes because of the heat coming off the circuit boards. We've revised the housing design and added fans to do a lot better there. I'll show some data there here a little bit. We also identified why I think some of the units were reading very low PM and probably not responding to some of the spikes that might have been existing. Found a bug in the code that if we had the right combination of things, we ended up kind of in a death spiral in the code, and it never actually showed to the filter that it should turn on. So that also seemed to have been addressed, but we'll talk about some upcoming testing. And I made modifications to our pressure measurements so that the circuitry has all of our functionality to be able to measure both differential pressure across the home envelope, which we need to actually run the system, but to have a parallel pressure sensor in place if we want one across the filter or across other parts of our system. I can get up to 4 differential pressure measurements on the circuit right now if we need. Anything past that, we'll have to use 2 nodes. So 2 requests of the team here. The first is if people would be willing to take some of these, what I'm calling like the outsider measurement nodes here in the next couple of weeks, that would be great. I've updated them. I'm not quite ready to send filters back out to people's houses, but these should have the fixed PM measurements and the fixed temperature things. So it'd be good to get some more in some other people's hands. The only downside to this is if I give you that and not the full system, you won't be able to see the values, but at least it will get logged. The second is if you have one of the filter units in your house, if you wouldn't mind bringing it back sometime in the next couple of weeks, I think we're ready to upgrade those, make some of these fixes, make some improvements from the first round of testing. So either if you drop it off or if you can let me know, I'll come by with the vehicle and pick them up. But I think we're ready to roll these upgrades out into a testing situation. We'll talk about 2 sets of data that we did as validation. We will talk about the pretty plot that I actually put some time into, and then the ugly plot after that. The plot on the left is the PM sensor that we are using is a fairly low cost sensor compared to a laboratory grade reference measurement. All of the kind of neon bright colors are co-located cheaper sensors. The green line is our reference sensor. These are fully uncorrected values, so we know they'll be slightly off because optical sensors are sensitive to the aerosol type, so we need to apply a calibration curve to them. But we are pretty repeatably seeing about a 3, that should be micrograms per meter cubed. At these ultra low concentrations, it's just truncating and saying 0, which I think is why in some of these kind of cleanish situations, we were always reporting 0. But after that, we get a pretty good linearity. So we actually are updating the code to use both mass and particle count. So the sensor does both. So I think we'll be able to recover those low range concentrations and do a little bit better there down low. Happy to talk way more on that if somebody wants at some point, but that's a pretty carousel nerdy conversation at some point. This is exactly what we're going to do. You come for training this afternoon. It's the same setup we did for this. The one on the right, which is not pretty, is I had 2 of our outdoor units, the blue and the orange, co-located with our weather station on the roof of the building using the new fan system to help keep the circuitry cool. And we're really good temperature agreement at this point. So I think the board heating issue hopefully has been addressed. One thing to note here, and something for us to think about as part of our installation, this is keeping that outdoor node out of the sun. The fan is not strong enough right now to overcome enclosure heating from solar radiation. So that's probably a longer conversation as well about if we can live with that, or if I need to go to a bigger fan, or if we add a solar shield. All things are doable, but the ones we have right now, that's kind of the extent of where we can get to with our current fan. And last is we have I'd say 95% working data pipeline for getting the data from houses to a point that people can actually use them. So the way the system works is data, man, I could not spell today. Data is collected by each node and it's transmitted to the central node. This is the touch screen. Then it gets stored there indefinitely. When we are in close proximity, so this is like in their house or in their kind of driveway, we can wirelessly pull that data onto a laptop. The idea of using a phone to do this is looking a little less promising. The laptop with a wireless connection seems to work. We don't need to have access to the home's Wi-Fi network. We can just tap into the network that we're generating internal to the sensors. We pull that data, and then I've written the script that when it finishes pulling, it then tries to push to a database that I've set up in our lab. So it can either push immediately then, or when we get the laptop back to the computer, or back to the lab, either way it will push data up. But what this does allow us to do, if we want, is if laptops in the field have access to the internet, either because we have access to their home, or we take a hotspot type thing, or we hotspot with our phones, we could push data immediately from the house to the database. And I am working on QA/QC scripts that as this data comes in, it does sanity checks on all the data. So if we had access to the hotspot, we'd actually be able to do that QA/QC essentially in real time while we are pulling the data, which I think has a lot of advantages to it for how cheap data is at this point. 2 requests here. Think about questions you would want to be able to ask with the data that we're pulling in, and we can start building that kind of processing the data in such a way that's easy to ask those questions. So I'm happy to do some of those things while we're putting together the data pipeline, just to expedite the data analysis process. I can't promise we can do everything, but I'm happy to hear your requests at some point. We'll try and incorporate that. The second is if there's additional data that we want to be adding to the database, now is the time for me to be building that in. We can always add it into the future, but my life is so much easier if I just build the database to do the things we want from the get-go as opposed to making modifications. Okay, that was super rapid fire. That is what I have so far. Do we want to go to questions?
Yeah, we're actually at time, but I'm happy to stay on a few more minutes for questions. So, if there are any questions.
So this is I've dumped a bunch of stuff in chat which you guys can look at, but Christian, just one of the things I've been pushing our team on is getting data from the field that we have now and integrating it rapidly, like immediately upon download. So I'm not saying don't do this, but as long as you have a time series of data, it can already be sucked in.
That's great. Yeah, I'm happy to do that. We could point the data to write to something else once we collect it. That's perfectly.
Yeah, because it might be like we have all the manometer data are high resolution and they're already being read in, and I'm sure you're capable of integrating it, but that might be just the extra work you don't need to do.
Good. To your question that I see in the chat in terms of data in CSV format, or is it still needs to be translated? So that kind of final push step is when I go from database, which if you're comfortable working with the database is easy, to a little more everyday toss in Excel type format.
Okay.
One of the challenges that we need to do is, because everything's at slightly different time steps, there's a bit of syncing of data that we're doing during the data merging.
So that's what our code does already. So yeah, so we just give us anything. That's what I'm saying. Like it's not synced. It's actually averaged in any tiny way you can imagine to get the right steps. So do what you want to do, but our code would be prepared to do the same thing, and then it just
Great.
dumps it all out to a CSV file that anybody can read. Like I'm not using R, Danny wants to use R, so it'll just go to a common thing that everybody can read.
Sure, sounds great to me.
Okay, now questions from other people.
A comment, this relates to what Ellison presented, not something I'd thought of until she was presenting, but that 100 CFM per 250 square feet compares, that's like 9 times what the assumed needed infiltration or ventilation rate is for a space of that size. Based on typical values of 0.35 air changes per hour, that would only be about 12 CFM compared to the 100, per 250 square foot space. And I think the difference there is that 12 CFM is assumed to be coming in clean already because it's outdoor air and it's kind of, coming in throughout. Whereas what that is saying is that's what you need to deliver 100 CFM of clean air when it's already contaminated and you're trying to push it through a filter. So it's an interesting thing to see that you need so much more flow when you're recirculating dirty air through a filter than when you assume it's clean air from outside.
I'm wondering, Paul, if their 6 air changes per hour got, that was slightly, I don't know if I would say misinformed, but too simplistic. I wonder if that got embedded in there.
I think they're also
Oh, you
based
mean that
around.
Joseph Allen had?
Huh?
You mean that Joseph Allen and those had come up with the 6 air changes?
Yeah, yeah.
Well, when it comes to the virus, the air changes per hour is totally the wrong metric to use.
I know, we
So,
know
so,
that, but they
but
don't know that, and then nobody, anyway. So Christian, you were gonna say something.
No, I was going to say, Allison probably knows this better, so she may correct me if I'm wrong, but I think some of those recommended rates were also based on the assumption that your source was continuing to be
Oh,
created.
yeah, like an ongoing, yep, yeah.
So you have to have more flow to keep up with generation
But so is
as
the
well as,
ventilation rates. It assumes it's about anyway. It assumes a continuous source. Yeah.
but when you're pressurizing the home, if you're doing it completely, there's no accumulation piece where if you undersize, because you're only like 60% efficient with any air exchange through a filter, because you pull some air in, you clean it, and then some fraction you're pulling in air you've already cleaned. I think it's an overshoot to keep up with generation, is where like those multipliers end up going up quite a bit. So I don't disagree with you, Paul. I think it is higher because this idea that you're re-cleaning partially cleaned air every time, as in addition to putting in new particles every
yeah,
time.
I think so. So 100 CFM and 250 square feet, that's 3 air changes, not 6. And another element there is you also have kind of a field you're able to pull from. I mean that it's pulling in air, but part of the reason it can only do 250 square feet is because you just don't get a pressure field from a single point recirculating fan that extends very far out. So, you get kind of past that room and it's not noticing that over in the room with the portable air cleaner, you got this thing that's spinning around itself.
Yeah. Okay. So I think I'm I have been beginning to see the need for a paper on just like exactly what the heck are you doing with different mechanisms, right? Because I think people talk about this stuff and it seems clear, but it's not clear to everybody. Can I call out something for possibly, this was never on your plate, human factors team, but Paul's question about what is it that we need to keep clean is something that's been kind of lurking, um, and is about to come out and bite us. So right now we're gonna assume we need the whole house to be clean, but there is this notion of you only need to clean one room, or you need to have a clean room, or you or some of the doors are going to be closed, which is another thing that came up in our field team discussions. So I think uh, this isn't necessarily on your plate, but it's something that we're gonna want to know from people, and I don't know how to get at that. Okay, couple more things. I think we're not having a meeting next week. But do remember that you are supposed to get your contributions to the annual report in by the 15th. Kristen will be bothering you. I have not a leg to stand on right now because I have done nothing, but I will meet the deadline as promised. So please take any time you would have dedicated to that or to our call to work on the annual report. Kristen, were we talking about filling in go, no go next week as well? Or just working on that?
Yeah, working on no or go, no go within like teams and groups on your own, not as like a full meeting.
Okay, so I'm not sure that everybody has access to that. I think the comms team may not.
Mhm.
But there has been, we probably needed to spend a little time giving directions on this. We're starting to develop a document about like, this must be true before we go to the field. And I think it's going to be staged, right? It's like this must, but anyway, we should start and look at that document. And Kristen, maybe you can help send that around. So I'd like everybody to at least take a look at that. Not everybody is here. Some people have more experience with it than others. I think Pi, you may not have been exposed to it at all. So there are things to do next week. We're just not having a call. Okay, and now we're really over time. Thank you all for the updates. It's looking better all the time. Many more of the problems we didn't know we had are fixed.
Okay.
I'll send
Well,
that
thanks, everyone.
via email. I can't pull it up right this second, so I'll send it via email and kind of share what it is.
Okay. Thanks, everyone.
Thanks, Christian.
Good weekend.
Bye.
Uh,